We're looking at volumes of revolution, which is chapter 5 of the Core Pure book 1. And the idea with the volume of revolution is this: if we have any old function, doesn't matter what it looks like, which is a function of x, then we know how to find this area here from a to b. That is the integral from a to b of f of x with respect to x, or if you prefer, the integral from a to b of y with respect to x, if this is y equals f of x. Now, one way of thinking about that integral is that it is like the trapezium rule, what we get when we split up this area into lots of little strips like this, and we add up all of those strips. So it's the same as, if I say this is delta x, the total of the y value at that point times by delta x for all of these different strips. Okay, so if we take delta x times y, we get roughly the area of this strip. Now, of course, there's a bit of an adjustment at the top, and that's not quite what we do in the trapezium rule, but it's sort of similar to what we do in the trapezium rule, isn't it? In the trapezium rule, we take all of these strips, we deal with each of them as a trapezium, and we say that area is roughly the same. We're going even more crudely here. That distance there times that y value there, or it doesn't really matter, that y value there, we're approximating so much, it doesn't matter whether we take this y value or this y value. But the total of y times delta x is the area of all these rectangles then, okay? Now, if we take all of those rectangles and we add them up, we get approximately this area under the curve. And then if I take the limit as delta x tends to 0, the total of all those rectangles becomes the integral of y with respect to x, doesn't it? If those delta x's get smaller and smaller and smaller, what I get is the area under the curve, and the limit as delta x tends to 0 is exactly the area under the curve, so it's the limit of y with respect to x. So what's important there is that we pick out this fact, that the limit as delta x tends to 0 of something or other times delta x is also the integral of that thing with respect to x. That's kind of one way of thinking about what an integral is, okay? Now, back in when we first met integration, I think it was in the first year blue book, the pure book, we had a different way of defining exactly what we meant by a definite integral, but it's equivalent to this. It was a limit sort of definition, okay? And this is the way we're going to think about it for now. And the reason that that is helpful is the following. We are going to think of not just finding this area, but we're going to think, well, what happens if I take my x-axis, my y-axis, and I take this curve and I spin it around the x-axis, and what I'm going to create is a volume, okay? Now, the way to think about that is like this. Now, apologies for my sort of slightly dreadful drawing here, but I'm spinning this thing round, and it's creating a volume that looks something like this, okay? So, x values go from a to b, I'm creating this volume, okay? Now, if I pick one particular x value in the middle, it doesn't really matter where the x value is, it's just to give us a rough idea, and I take a little strip which is delta x wide, and then I spin that around the x-axis, then I'm creating a little sliver like this, aren't I? Okay, so can you see that what I've got there is a little sort of disc? And when I say a disc, mathematically this is obviously a cylinder. So that height there is y. So we know how to find the area of this circle at the end. That is y squared. That's the area of the circle. And then this is a cylinder, so a cylinder is a kind of a prism. So y squared times delta x is the volume of that red disc that we've made there, because that disc is a prism. Area of a prism is volume of the, volume of a prism is the area of the cross-section times the perpendicular height. Area of the cross-section, is y squared times pi, missed out my pi there, y squared times pi is the area there, times by delta x, that gives me the volume of this little disc here. Now, if I did that all the way along, I split this up into lots and lots of these things, I would be taking the sum of y squared times pi delta x, okay? So what I'm saying is that that volume there is approximately equal to the total of pi times y squared times delta x, where delta x is some little increment in x that I've chosen. Now then, if I take the limit as delta x tends to 0 of that thing, I'm going to get the exact value of the volume. And we've just said that the limit as delta x tends to 0 of a load of sums like this, of a sum like this, is the integral. That's what an integral is, or is one way of thinking about an integral. So it's the integral from a to b of pi y squared dx. Now, because there's an integral and pi is a constant, I can just pull the pi out the front, and that is where our formula for volume of revolution comes from. Okay? So if I want to see what is the volume of this thing, if I take that area AB and I spin it around the x-axis, I want to know that volume. The way I do that is integrate from a to b y squared with respect to x. Let's just have a look at an example and see exactly how that works. If I take the function y equals 9 minus x squared, I'm taking example 1 from page 73 here. I've got y equals 9 minus x squared, and I want to know the region which is bounded by the x-axis, the y-axis, and this curve when I rotate it around the axis. So if I sketch this graph, it looks like this. It's a bit of a dodgy sketch. There we go. Look, it looks like this. Now, if I find out the point where it hits the y-axis and I find out the point where it hits the x-axis, well, it hits the, well, actually you don't need to know the point where it hits the y-axis. I know that the value of x on the y-axis is 0, so my a equals 0. If I find out the point where it hits the x-axis, then that's going to give me my value of b. And we can see that from the, if we use the difference of two squares, 3 minus x, 3 plus x, and put it equal to 0, then this is going to be 3. So b equals 3. So what I need to find is the integral from 0 to 3 of y squared with respect to x. I'm just using the formula there. So the volume of revolution is pi times the integral from 0 to 3 of y squared with respect to x. So that's going to tell me, if I take this shape here, rotate it around the x-axis, what's the volume? What does that look like exactly? Well, integral from 0 to 3 of 9 minus x squared, that's y, 9 minus x squared. Then I've got to square that and integrate that with respect to x. So that is not too bad an integral to evaluate. Just for the record, what we'd do is we'd expand the brackets there. So that's where we get our 81 minus 9 times x squared minus 9 times x squared, so that's minus 18, lots of x squared. X squared times x squared is x to the power of 4. Negative times negative is a positive with respect to x. So I'm integrating that with respect to x. And from that point onwards, I'm just going to refer you to page 73 because we are onto a fairly straightforward integral. Notice the pi stays at the front of these square brackets. It's probably the simplest way to do it. Here's our integral from 0 to 3. Substitute in 3 for the upper limit, 0 for the lower limit, do the takeaway, times by pi, and there is your volume. Okay, so that is volumes of revolution about the x-axis. That's how they work.